So, but then I'm kind of an old guy, so
I run to the bathroom.
I'm recording right now. Yes, Jake. Go ahead. Why did you?
Well, I was just wondering.
Okay. Yes.
We're like right now?
Because
Right.
if you write something embarrassing, we're gonna have to call you out.
Oh, I got you. That's true.
We
Yes.
got one.
Now, whether I actually publish this video
Oh, I'll
on the
make sure.
website,
Oh,
that'll
make
be
sure.
that'll be
Just
another
have to
thing.
ruin your next class.
Okay. Yeah. Yeah. All right.
If Matt says something funny about chicken again, you'll have it.
Well, that see now that was good. I do wish that was recorded. I gotta admit.
Yeah, that's
All right.
my bad.
So now what? While we have this up here and is we wait a little bit for Jacob to get back, but let's look at C. I mean, let's read part C here. It says, let the base. So notice the difference in the wording here. Okay, in part B, it talks about the volume of a solid revolved. So all of the solids we've done so far, we've said take this region and revolve it. Okay, well, what that does, whenever you revolve the region, that is going to create slices that are either going to be one of these two things. You're either, when you revolve it, just the process of revolving it creates a circular object. So the slices are going to be circular, and the only two types we will deal with are solid slices, where the object is solid all the way through, or there's empty space, so the slices will be washers. So those are the only two types of slices we can get when we do a solid of revolution. Okay? So we'll be adding a little something to our notes here when we get to this. So what we were just doing, Jake, we were just talking about the difference here between B and C. So in B, so whenever you see the solid generated or the solid is going to take a region and revolve it around an axis, automatically it's either disk or it's washer. All right, so what other kinds of solids could we have that had different kinds of slices? Now I use the word slice. Usually the word you see is cross section. Same thing. Slices and cross section is the same thing. So these are a little different. Let the base of the solid be the region. So now, instead of taking this region and revolving it, the region is like the base of the solid. So that's like sitting on your desk, that is the region, and the solid is going to grow up off of the page. Okay? All of the cross sections then, so we've got this base region that's between some curves, and then up off of that is going to grow this object that if we slice it this way, or maybe slice it this way, okay, is going to, all those slices are going to be a certain shape. But they wouldn't have to be circular shape. They could be all kinds of different shapes. Now we're going to focus in on just three of them. So this says if all cross sections perpendicular to the x-axis, so they always tell you which way. Are you slicing this way or are you slicing this way? Okay, I misspoke. It's not slicing this way. It's slicing this way or it's slicing this way. Okay? If all cross sections, yeah. I mean, because if you had some weird kind of parabola shaped region, you slice this way, all the slices would be that parabola. Yeah, well, no, usually what it'll say is perpendicular to the x-axis or perpendicular to the y-axis, which is the same thing. But it'll use the word perpendicular. So if all cross-sections are perpendicular to the x-axis and those are squares, then set up an integral that gives you the volume of this solid. So this is, I've found very helpful. So this is what we're talking about. So here is our region. This particular region is going to be the area within this equation right here, which is the equation of a circle. Okay, so here's our region. All right, just like we've had these other regions, just like in the last problem, we could have just as easily done any of these be our region. Right here, this could be our region. Okay, and growing up off of this is our solid. Okay, so we got to think of that region laying down flat on our paper. All right, so this is going to actually look, this is going to be 3D. Now, the problems you do aren't, but no, because the slices, now it says that the slices are going to be perpendicular to the x-axis. So this is not problem, the problem we were just doing, but it's similar. The one we were just doing said the slices are going to be squares. That's what we're going to do. So these cross sections are going to be perpendicular to the x-axis. They're going to be square slices. Okay? So the first thing we're going to do is take our region.
Wait, we're doing square slices of that?
Yeah.
Of the circle?
Yes. Now the circle again is the base. This is the base of the solid.
So this is like we are looking down.
It's like we're looking down at it, right? I'm going to lay it down here in a second. Okay, we're going to lay it down here in a second. So first thing we do is we put in some strips, right? Now usually we'll just put in one strip, okay? But it said perpendicular to the x-axis, so there they are, perpendicular to the x-axis. Now remember, we got on a circle equation, you got the top half and you got the bottom half, right? That's the plus or minus, okay? So this part up here is the top equation, this down here is the bottom. Okay, here it comes. This is cool. Okay, so there we go. So we've laid that down. So that is our base. The solid is going to come up off of that. Okay? Now imagine now squares coming up off of this. Now think about
Squares and not circles.
it. Could be whatever we want.
But squares
A
don't
ma-
fit a circle.
Sure. This chord right here. Again, what you got to, it doesn't matter. It doesn't matter. I could take a bunch of squares and set them down on this floor, right? And I could take a bunch of semicircles and set them down on this floor. And whatever, and those will create different shapes. Now, what are the sizes of the squares? The size of the squares are determined by these lines. See these lines right here? For example, over here, how big is a square going to be? Compared to one over here. These are going to be bigger, right?
We're not.
This strip,
It's not.
this strip is one side of the square. Squares are going to be coming up off of this circle.
Just show us.
I want to show you. I'm going to show you, but I want you to try to visualize it.
Okay,
Just like it
okay.
says right here.
Yeah.
Do you see
No,
it?
I don't see
I
it.
know. Well, keep trying.
I'm
Okay.
trying. I
So
just
like
want
the
to see.
y-axis is the floor.
Yes. The y-axis is the floor. Y and x-axis.
Well, the x and y axis both are on the floor. We had an x and a y axis here. We got a circle.
Just bend it
On the
we can
floor.
see it better, 'cause we can't have the
And then you're gonna have squares coming out of the circle.
All right. Here we go.
I just keep trying to see it.
There they are.
Oh, okay.
That made more sense.
I was trying to see it in 3 dimensions. That's not even a square. Those are
I thought it was
What do you mean
supposed
they're
to
not
make.
square?
I thought it was
Of course
supposed to
they're
make a
square. Well,
solid.
It's skewed
It's good.
because they
I thought it was supposed to make a solid.
It's good.
It's going to make a solid.
Yeah. These are just four. It's like a lemon. We just take a few slices. This is just a few slices.
Okay, how do you know how far up the square?
How do you know how far up the squares go? The
Well, it's a
squares.
square.
It's a square. All the sides are the same. So right here, this strip here is pretty small. All the sides have to be that same side. In the middle, they're a lot longer.
But they look like
So that's why it goes up.
Alright.
Why do they look like
It's because
rectangles? I don't think they
They
do.
had to do the y-axis at an angle so
Yeah,
you
it's
could see it.
tilted.
Otherwise,
Yeah.
they would just like look like vertical lines.
Yeah, exactly.
If they
This,
put the y-axis perfectly straight down, everything would just look like lines.
right. This looks like an acute angle. This is not. This is a right angle, right? Okay. All right. So now, here, let's try this. See if this helps.
That helped.
Oh.
Well, keep that going.
Good
Just
go.
anytime. Anytime.
Do the sweep.
Okay. Okay. All right, now. All right. Now, the way you guys on all the problems you do, you're going to be always be seeing that view right there. Flat. It's going to be flat. You have to use your
Well, I'm gonna
imagination
draw
to
like
refer
that.
back to this, or you can draw this if you go. Okay, let's sweep one square. Okay, so it says you got it. Okay, we're getting better. We got it. Okay, now here we go. Notice how these edges are moving around the circle. It's getting bigger because they're,
So,
right, the biggest one's in the middle,
if we had an infinite number of squares,
right?
would it become dumb?
Well, I don't know. What do you think? This is what we're
Yeah.
saying. Then you describe it. And that's what this is representing. This is all the different squares. So if we took this infinite number of squares, these are the slices. We're slicing it this way, right? Perpendicular to the x-axis. So can you kind of create, it's a dome. It's kind of coming up like this. Flat on the top? Is it flat on the top?
It would be Not that all squares.
It's gonna be domed coming this way, but across the top this way, yeah, it'll be the top of the square, so that part will be flat. Right, so it won't be a circular dome, it won't be a sphere, like half a basketball though, right? What about this side, what about the sides? Aren't the sides over here straight up and down? The sides are kind of straight up and down, okay, let's do it.
How can you relate it to?
See, here's the part a lot of people don't notice is this part. See those black lines? What are those? Where's that coming from? The corners of the square, right? There's the corner and the corner. So the corners of the squares are making that. But now those corners are coming in because the squares are getting smaller and smaller.
Whoa,
See, I wish it
whoa.
would have stayed there.
Yeah, I would
Well, we
like.
can do that. We can do
Oh, so it's like this Australian building.
So this is straight up and down here, right? Kind of like the wagon cover a little bit, right? A little bit, except for the fact that it's coming in, you know, on the sides here. So it's rounded going around, right? It's rounded because of the circle, obviously. Well, yeah, that's what we should get into, yeah.
No, we have one. We have one. They have one out in the shop.
Yeah.
Yeah. He printed his own, phone district plug for the stuff.
Yeah. Spencer Shield brought a thing one day that he printed. And then we can put the four, you know, there's the four squares that we had earlier in there. And then
I guess at this point I kind of.
there's the squares.
I've come to terms with. I'm just not gonna do it.
Not be able to see the thing. So,
Whoa, whoa, whoa.
okay, so now after having seen that, yeah, I mean, let's talk about how to do it. So after having seen that, when we draw our strip in here, now the strip, remember, we're told in the problem is perpendicular to the x-axis, okay? The slices are here, right? Now you can imagine, here's those squares coming up off the page. So when we slice, we got these squares. This strip now is what?
The
No.
length of the
The
square.
strip is one side, oops.
All sides.
Well, right, because the square is the same. But I mean, this particular strip right
But
here,
What are you talking about? It's two.
this particular strip, just squint so it's fuzzy. This, this particular strip is what? One side of one of the squares, right? So, what did we say
We
in
got
our
apple
notes?
up and take them times.
What did we say in our notes is the volume? It's this right here, right? It's the area of a slice times the width of a slice makes the volume of the slice. So what we need is the area of our slice. Well, what did we say our slices are? Squares. What's the area of a square? The area of a square is side squared, right? Just a side squared. Well, what is this strip? This strip is one of the sides. That easy. So in this particular problem, what would be the strip? It would be the top y value, which would be square root. This has a radius of 2, looks like. So this would be square root of 4 minus x squared. That's the top half, right? The top half of this is y equals square root of 4 minus x squared. The bottom half is y equals negative square root of 4 minus x squared, right? That's our equation. So it's going to be the top y value minus the bottom y value. Right? So everything's the same as what we've been doing, which is really just 2 times the square root of 4 minus x squared. Right? So again, everything comes back to, yeah, being able to see the solid and all that stuff in the end is really not that important. Okay? It's nice, absolutely. What really is important is, okay, it's a base. The region is the base. So you got to remember, okay, that's just the bottom of the solid. The solid is coming up off of that base. What objects are coming up off that base? What shapes, in this case, are squares. So you draw in your strip. It all comes back to the strip. You draw in your strip and you ask yourself, what part of the shape is that strip? Oh, this strip is one side of the square. You got to remember this, right? So what have we done so far? We've got pi r squared in there. We've got the washer, pi times r squared minus r squared in there, and now we've got a square area in there, which is just s squared. So all we have to do is take our s, stick that into the integral. So the integral is going to go from what to what? Negative 2 to 2 is what this picture goes from. And then it's going to be s squared. So 2 times 4 minus x squared, and all of that squared. There is no pi in this, right? Because this strip is not, we're not doing circles. It's not, right?
So wait, is that like a generic
This is a generic formula. This is the generic formula we're using, right? I mean, we go back to this.
Oh, sure.
Anytime we're doing slices, and I'll come back to our notes, we'll add this in a minute. Anytime we're doing slices, which is what this is, our formula is this. What is the area of the slice? Well, so far we've had circle slices, we've had washer slices, and now we just added square slices. Okay? So if you wanted to put this in your notes, I've started kind of a new page here with types of slices. Trying to make them somewhat three-dimensional here, but, ooh, I'm proud of that. That's not bad. On this thing?
Yeah.
We have a disc, we have a washer, and we could have square, and we could have square slices now, right? But again, square slices are going to come in a different type of problem, right? Circle slices, this is what we're talking about at the beginning, are going to be in solids of revolution. Not that that's important, you just have to identify the slices. But the problems we've done so far have said revolve the region. Well, anytime you revolve the region, you create circles by revolving. So that's where you get disc and washer. But now we're talking about slices that come up off of a base. Different types of solids, but we can still, it's the same idea. The integral is adding up the volume of all the slices. So the square is s squared and then times whatever. Okay? All right, so that's how, but again, it comes back to the strip. Now, let's look at,
You do like an A-shape?
well, pretty much as long as you can do find the area of it, and then it has to do with the strip. So it's a little bit limiting, but there are some other ones. Now, let's see, let's go ahead and do this one now. Let's go ahead and do this one in your packet. Okay? C. So back to the picture, we had 3 cosine, which came down like this. We had e to the x squared, which came up like this. So we had a region here. And this was 3, this was 1. And what did you say this point was? This was 0.836. It rounded to, is that point right there. Okay? And so this says that this is now the base of our solid. Right? Instead of taking this and revolving it around, it says the base of a solid, let the base of a solid be the region R. If all cross sections perpendicular to the x-axis, so right away that tells you your strips are vertical, right? Because it said the cross sections are perpendicular to the x-axis, so that means vertical. All of those cross sections are squares. So what do we imagine? We imagine squares coming up off of the page, right? Down here they'd be smaller squares. Bigger squares over here, right? Smaller squares over here. So this strip is what? One side of the square that's coming up off the page. And so instead of writing R, we write,
Just top line.
it's right S, and so it's this strip. So yeah, in the last problem we had empty space because we're revolving, we were doing big R minus little r. Now we just want that strip. Well, that was top Y, which was 3 cosine x, minus bottom y, which was e to the x squared. That right there is that strip. Now when we want to do area in part A, all we did was the integral of that. because we were doing height times width, which is area. That gave us that. Well, now we're doing volume. Right? So we've got these squares coming up off the page. So the area of that is that squared. So it's 3 cosine x minus e to the x squared. And there's always a way to get people that get confused with these sometimes, because now look what we're doing. We're squaring that whole thing. In part B, it was this squared minus that squared, because we were doing big R squared minus little r squared. That's why I think it's so important to write that stuff out. Write out what big R is. Write out what little r is, right? Then you follow your formula. So our integral is simply our strip squared. This is one side of a square. You square that, you get the area of the square. This gives us area of the square times the width, gives us the volume of the square, and then the integral adds it up, 0.836, and you got it. Okay? So it's just a variation off of that. So now, all we need to know is what other types of slices could we run into. So let's go back to this. And another one that we sometimes run into is equilateral triangles. That's another type of slice that we're going to have. Okay?
So
Why don't we go ahead
base
and
of the triangle.
let's go ahead and put that into our notes here. So another type of slice would be an equilateral triangle.
So the strip is all sides of the triangle.
Since it's an equal, that we stick with equilateral because that's easier to do. Now the problem is, what is the formula for an equilateral triangle? No?
No, it's height.
Well, let's do it real quick. Well, the problem is base times height we're not going to know. We're going to know the base, if we call that the base. But then what's the height? Well, remember, this is coming up off of the page, right? These triangles are going to be coming up off of the page. This will be the strip, right, that's laying down in there. But then what is the height? That's not part of this. So what we have to do is we have to get it in terms of this. Well, here's what we can do. Since it is an equilateral, we know that's 60, we know that's 60, we know this cuts perfectly, 30 and 30. Now we got to go back to our trig. So this side over here would be 1/2 the base. If 1/2 the base is over here, across from the 30, what is this over here? Remember the ratio in the 30-60? 30. Yeah, this is 1. Oh, you guys did it this way. You guys did, this is 1/2. This is 1.
Yeah.
Yeah.
This is √3/2, right? And that's your ratio. So if this is 1/2 the base, then this is just B, and then what's this? Times base, right? In other words, they're in this ratio. So this is always √3 times this one, right? Oh, wait a minute. No, that'd be √3. Yes, that's right. That's right. Yeah, it's √3/2 times whatever the hypotenuse is. So √3/2 times base. So now what is the area? So now the area is 1/2. Our base is B, and our height is √3/2 times B. So that's √3/4 times B squared times B squared. So back to our previous page, that is actually the formula. Now I called that S. I thought I'd just keep calling that S because it's the strip. So we'll just keep it consistent. So it's going to be √3/4 times S squared. Now that's kind of interesting because, so if you do a problem that has square cross sections, it'll be the same exact integral except a √3/4 out in front, right? Because it's whatever the strip is, but then times √3/4. And so you put that out in front. So it's going to be very, very similar. So if we go back to our problem here, so if we lay that flat, okay, put our strips in there, Okay, now picture the equilateral triangles coming up off of there,
Okay.
right? Alright. Rotate that. Okay, now instead of squares, but again, it's all based on what this strip size is. This strip is a side, and since it's equilateral, that makes it easier. So that keeps us away from two variables. Sometimes I've seen problems on the AP test where they say that the slices are triangles of height 1. Right? Triangles of height 1. Well, what's the area of triangles of height 1? Half the base times the height, right? Well, if the height is 1, it'd just be half times the base. And what's the base? The strip, whatever your strip is. So when you do your top minus bottom, that's your strip, that's your base. The triangle area would be half the base then. Because half the base times the height, and the height would be 1. So instead of it growing like this, it would just stay at a height of 1 at a time. But the triangles would get really flat. You know, the base would grow, but the height would. So I've seen on the AP test them do different, or they'll say the slices are rectangles of height 3. Right? Well, what's the area of a imagine a rectangle coming up off the page, but if all of them, they were all height 3, what's the area of a rectangle? Base times height. So what's the base? The strip times 3. So it'd just be the strip times 3. Right? So you can have variations off of this as long as they give you enough information so you only need the strip. Right? And again, it'll all come back to that. Okay, so if we show the solid, so if it slides through there, like so. Now you've got that single edge up on top because of the top of the triangle. Yeah, I was going to say it's like one of those conquistador helmets. Okay? And so, you know, you've got your triangle in there in the solid. But again, the integral's adding up the solid just the area of the triangle times the dx, the width of the triangle, gives the volume of the triangle we added up. Okay, the last one we're going to have is going to be semicircles. Coming up off the page are semicircles. In other words, yeah, this would be more of a dome kind of thing. Now here we've changed our region, right? The first two we did circle regions. Of course, we did that other odd-shaped region. Here, let's say we have this region. So they just give us a line. Okay, let's see, what's the slope of this line? Let's see, rise is 3 over 4. So this would be, and then it's down here. So we could write the equation of this line, which we'll do here in a second. This time, the slices are going to be perpendicular to the y-axis. So the strips are going to be horizontal, which is no problem. We'll just do right minus left. So we'll have x, have to solve for x. Okay? All right. So we drop that flat. Imagine now semicircles coming up off of there. Okay? Like so. All right? So you can kind of see what's happening. Now remember, there's a right angle back here. So it's not like a cone. Some people think half of a cone, but you know, a cone kind of comes in from both sides. This has a right angle on one side, right? Well, it's not quarter of a cone, because if you quarter that, then it's quarter circle. It's still half circles, right? So it's kind of a slanted, weird kind of cone. So it would be something like this. Right? But it's still kind of that cone kind of shaped thing, just with that right angle on that one edge. Because half a cone, they'd be both be coming in like this. This has a straight edge here, and then this side's coming. Okay. But anyway, so the idea is then back to the strips. Okay. Now there is a difficult part of this one. And that is the sense, let me reset that. Okay, so we see the semicircle. What are the strips now? What part of the semicircle? The diameter, right? The diameter. And so this is a part that we sometimes mess up, and let me show you what I mean. So coming up off of the page, so here's a strip right here. Okay? So this strip is the diameter of that semicircle that's coming up off the page, if I want to try to draw it, whatever. But Okay, that's the diameter. Now, so I'm going to call that D. All right, now that diameter is what? It's right. Now, what was this equation? I think this equation was y equals, it's 3 up and 4 over, so 3/4 x, and it's got a y-intercept of -3, so it'd be this. But remember, we need what x is, right? So what are we going to do? Multiply everything by 4 maybe? You get 4y equals 3x minus 12. That'd be one way to do it. Add the 12 over to the other side. You have 4y plus 12 equals 3x. Now divide by 3. So we'd have x equals 4/3 y plus 4. Is that what we get if we solve for x? So it's going to be, so my diameter is this x coordinate, which would be 4/3 y plus 4, minus this x coordinate, which is 0. That'd be my diameter. Now remember, what goes in the integral? Hang on here now. What goes in here? The area of the slice, right? In here we need the area of a semicircle. What's the area of a semicircle? 1/2, a little nervous by how hard we had to think on that. 1/2 pi r squared, right? Semicircle. Half of a circle, right? So we need 1/2 pi r squared. Do we know what r is? It's half of that. Now here's, for some reason this throws us off. There's half in here twice. No, we can't do 1/4 because
That's just.
it's r squared. So we got to take half of that. What's that? You could. No, it wouldn't be that. It would be
1/2 pi. 1/2. Well, 1/2 pi because you go out times r.
Look. What's another name for r? 1/2 d. Okay. So what is that? That's 1/4 d squared, and then times the 1/2. So this would be 1/8 pi d squared. Now I don't care how you want to do this. It's totally up to you. If you want to remember it that way, if you think you can remember that, 1/8 pi d squared or 1/2 pi r squared. The problem with 1/2 pi r squared is once you have the d, then you probably need to write the r, which is 4/3 y plus 4 all divided by 2. Now you can divide each of those by 2. That might be simpler. Then you have to, where I've seen people have difficulty is they get this and then they take half of it. They plug it into this, but then they forget this half, right? And they forget that there's half in there for 2 different reasons. This half is because we have a half a circle. This half is in there because we're taking half the diameter. So if you'd rather just memorize this formula, it might be smarter. Because think about it, every time we do one of these problems, isn't the strip going to be the diameter? Whenever you do a semicircle, this strip is the diameter of that. So it might be smartest to remember the 1/8 pi, which can come out in front, and then the d squared. So then we can do the 4/3 y plus 4. Here's the other thing I like about that. That keeps consistent with what we've been doing. Every one we've done so far, we've taken the strip and squared it, haven't we? A square was the strip squared. The triangle was root 3/4 times the strip squared. And the semicircle is 1/8 pi times the strip squared. Right? So every one of those problems, that problem we did earlier with the square, we could have just done s squared, and that would have been for squares. Root 3/4 would have been for equilateral triangles. 1/8 pi out in front would have been semicircle. Okay? Whatever. You've got to know these formulas. So, going back to our notes. And then the strips started down here at -3, horizontal, and they went up to 0. So that would have been -3 to 0 on the integral. Okay, so back to our notes. So the last piece, the last slice we're going to have to know is, geez, I don't even want to draw these again. Third block. That's a good question. I should save it from year to year and not even read it. Okay, so what are we saying? So our area, so this is a semicircle. And so we can either go with 1/2 pi r squared or we can go with 1/8 pi d squared, or yeah, you could call it s squared if you want, you know. You can call it s if you want. I call it d because that strip is the diameter, right? I like s because not just strip, but side of a square, side of a triangle. We don't really call that a side on a circle, okay?
It's the side of the semicircle.
It's, okay? So, but everything's about the strip. Here the strip is the radius. Here we drew two strips, right? One is big R, one is little r. Here the strip is the side of a square, side of a triangle, diameter of a semicircle. And it's always, to get the strip, it's always top minus bottom, right minus left. You write that out, set up your integral, and you got it. All right, so we've seen how that's in some of the homework problems, or in some of the packet problems. There's your homework today. These are in the LH packet, same LH packet. You just skip another page ahead, I think, from where you were. And they actually draw the pictures for you. They draw the three-dimensional part of the picture. And to be honest, I almost think it's more confusing than if you don't have it. So here's what I would look. Why don't we just do the first one together? Here's what I would recommend that you put on your paper. So 49 A, B, C, 50 A and B, 51 A, B, and C. Now, what happens is 49, 50, and 51 are all different regions, and then the A, B, and C is, okay, one is with squares, one is with triangles, you know, and so forth. Okay? And once you get one set up, you know how this is going to work. Once you get the strip set up in one, the integral setup is going to be very easy.
Nice.
Right? So then it's going to be a matter of just going back through our old packets and practicing some of those.
I don't even want to do the intersection.
All right, page 421. Oops. What happened here? Okay, there it is. All right, so what I'd like you to do on number 49 on your paper, yes, they've got this here, but the way you're going to do most of these problems as you're learning this is let's read the problem here. It says, okay, 49, find the volume of the solid whose base is bounded by the circle x squared plus y squared equals 4. So let's draw that circle, right? And it's a radius of 2. So this would be 2, this would be -2, you know, like so. It says the cross sections are taken perpendicular to the x-axis. So they're going to be vertical. So in part A, we're going to do square cross sections. So I would want you to draw one strip. So again, they've given you the picture, and of course we've already seen that. We saw this picture, in our on our sketch pad on the computer visualization we had, same pictures. All right, but let's just draw in your one strip. This is how you would work them. And now that one strip's going to fit you. That's going to work for all the three problems on 49. Matter of fact, we'll probably be done and you have time to line up even. So what do we got? Well, what information do we need here? We need what y equals. We need to solve this for y, don't we? Okay? So that's just going to be root 4 minus x squared. Wow, it's the same one we had, isn't it? Almost exactly. I didn't even realize that. That's good. Okay? And that's y equals negative. So, for part A, so if we wrote here our strip in part A, that's going to be, what did it end up being? It was root 4 minus x squared minus negative root 4 minus x squared. Simply top minus bottom, which was just 2 root 4 minus x squared. Right? So that is our strip. I mean, I don't want to rush through this here. But I don't want to offend anybody by rushing through it. But so you've got 2 root 4. That is the strip. So now think about it. So now you do part A, squares. Okay, so what is that? That's one side of the square, right? So you'll square that. Equilateral triangles, that's one side of the triangle. Semicircles, that's the diameter, right? That strip right there is the diameter of the semicircle coming off the page. You got your formulas? Away you go. Set them up. Now here you're supposed to set them up, actually get them.
Or do we just have?
Yes. Well.
I
Yes,
know,
I would
I
like
just
to.
wanna know what we're doing.
Okay, good. So yes, set them all up and put them in your calculator. So,
I'll do that later.
which you certainly can. Yeah. 128 over 3.
Sounds good to be familiar.
I wonder why.
Yeah, that is. Yeah, that was one yesterday. wasn't it?
We don't, put anything out front on spread.
Yeah, right. Right, nothing
And then
out
I can
front.
just take that same number and multiply that times 3/4, right?
Can we? Or
Yeah.
Well, I would like you to rewrite the integral. All it is the same integral with a root 3 over 4 out in front, isn't it? Yeah. Right? And that, again, you want to do that. I think the act of writing that down is going to help you remember those formulas.
I don't know what's gonna help me, but it's gonna take a while.
Well,
Well,
I'm trying to come up with anything I can.
Do you have any more children's toys?
Would that be helpful? Something bring it back to real life.
the answer to the second one,
And then, and most of our practice, our book hardly has any of these in it, and the packet doesn't have very many, but we've got some in our packets like we've already seen, and so we'll be going back and finishing those, and that'll kind of be how we review these. Tomorrow is going to be packet work time for an hour in our new packet.
Wait, how do we do isosceles, right?
On
your calculator. Is
Yeah.
that right? Usually your phone can make it till noon,
We'll say.
Wait, how do we do isosceles, right?
which is strange since you're not allowed to use it in school.
Since it's
always turned off during school.
Well, we're just doing A, B, and C. Oh, I
Just doing A, B, and C, yeah, yep, just A, B, and C. Yeah, and, I mean, isosceles right triangles would not be that hard, but it's just another formula we just chose. The ones I've seen in the AP test have almost always been semicircles, equilateral triangles, squares, or like I said, rectangle of height 3.
So they're not gonna have like the isosceles right triangle.
I've never seen that one in a,
So if we see it this year, it's gonna be your fault.
it'll be my fault. You can blame me.
As long as I can blame it on
They're
someone.
Yep,
not
yep.
gonna care.
Blame me. Huh?
They're not gonna care. Well, Mr. Clark didn't. Like tough.
Yeah, write him a note on the AP test. You can say,
Every single problem my teacher did
my
not
teacher
teach me.
sucks.
So you have to cross it out so it doesn't count.
Yeah, if we cross the problem, does that mean?
Yeah, you cross the whole problem. Yeah, they'll ignore the whole problem. No, I don't think that'll work.
what was the last one you were doing? 51. Right? 51.
50, yeah, 51. 51 A, B, and C. 50 was just A and B.
It's only 11:23.
Wait, so the diameter is the
It's
strip.
down 8 minutes. Should have been packed up like a
What's that now?
The diameter is the strip.
Yeah, because what you have is, well, this semicircle, here's your strip right down here. So see how that's the diameter? Yeah, so the semicircle is coming up off of
Got it.
the.